Today we're going to go over 10.1 parametric equations. Basically, we've been working with everything in the Cartesian plane or the rectangular coordinate system. And in that system, we know how to find locations of a graph or how to graph using X and Y coordinates. But now we're going to be dealing with parametric equations. And parametric equations deal with three variables. We now have three ways to describe the graph or work with the graph. So our first definition will be if f and g are continuous functions of t on an interval I, then the equations, I didn't realize I spelled that word so wrong. Then the equations x equals f of t and y equals g of t are called parametric equations, and t is the parameter, okay? So basically, we're going to be able to work with a lot of other shapes other than just plain old functions at this point. The main thing we are noticing here is that we're still working with X and Y, but now X and Y are both being described as in terms of T. Okay, so in general, you guys, I'd like you when you're doing this to use 5 values for your T. And you know, pick, if it's worth sine and cosine, you probably want to pick values that you can do quickly in your head. In this case, I'm just going to pick -2 to 2 and count by ones. So I'm going to draw this little table right here. I'm going to make myself a little table. And in my table, I'm going to have T, I'm going to have X, and I'm going to have Y. Okay, so for my time, I'm just going to pick -2, -1, 0, 1, and 0. Okay, oops, sorry. 0, 1, and 2. So what you do is you find out what would your x be when you let t be worth -2. So we would get 4 plus 4, which would be 8. What would your y become? Well, your y would become -1. Okay. Now, you should probably pause the video, go through and fill out this table and make sure that you and I end up in the same spot. Okay, hopefully you guys unpaused it, and we are now at 3, 0, 0, 1, -1, 2, and 0, 3. You can double check me on all of those, but hopefully that's good. Okay, so now we want to be able to graph this. So we're going to come over here. And we're going to try to graph this parametric equation. I'm going to go 2, 4, let's go a little bit more out here. 6, 8, and let's go 1, 2, 3. Let's go -1, -2. Oops. So we're going to go -1, -2, 1, 2, 3, so on and so on. Okay, so now I'm going to try to graph this value. I'm going to try to graph, and this is still my X and Y coordinate, right? So I'm going to graph the point 8, -1. So let's do this in green, 8, -1. That would be like right around here somewhere. Okay, let's do the point 3, 0. That would be here somewhere. We got the next one is 0, 1. That's going to be here. -1, 2. Let's do -2 over here. So then -1. So we're going to go -1, 2. So -1, 2. That's right about there. Right. And then, geez, I don't know. Let's do this last one, 0, 3. That's right about there. So let's connect the dots. And we have our parametric curve. Now notice I didn't draw arrows. I didn't draw arrows to say this goes on forever because this is just the particular window I decided to look at. So in this location, I have it kind of looks like a partial parabola. The other thing I would like you to do is I would also like you to give the direction that you think this is traveling, okay? So you always start with the smallest time frame and work your way to the time frame. So we're at -2, -1, 0, 1, 2. So start with the smallest t and work your way to the largest t. I shouldn't say time frame, but I just mean the smallest parameter and work your way to the largest parameter. So we have t equals -2, -1, 0, 1, and 2. So I'm going to say, well, when was t equal to -2? That was here, right? That was at -8. And then where was my next value? 3. So you guys see I'm going in this direction. Everyone would agree I'm going in this direction. Okay, so that's one of the differences you'll notice is depending on the situation or the time you ask me, when you say t is equal to 0, well, I'm right here. So if I'm only going from -2 to 0, then I only have this portion of the graph. I would only have that portion. You know what, let's do this in a highlighter. I would only have this portion of the graph, okay? So hopefully you guys understand that the parameter dictates how much of the graph you're gonna get to see, okay? So let's take a look at, okay, so let's look at another problem. Let me have you guys work on this one. So you guys try x equals t squared plus t and y equals t squared minus t. So draw your little table. So this is my t, this is my x, this is my y. And I would say again, oops, plot the following. Okay, so you're going to plot this parametric equation. So take a minute, pause the video, and see if you can fill out this table. Why don't we use the exact same t values, -2, -1, so on and so on. Okay, so I'm back, and hopefully you guys plugged in 1 for t, so that gave us 1 plus 1, which is 2. And then for y, this gave us 1 minus 1, which is 0. Let's see here for 2, we plugged in 2, and we got 4 plus 2 is 6. For here, we plugged in 2, we got 4 minus 2 is 2. So I think we're okay. So let's look at this now. Let's draw a graph. Okay, oops, it's kind of crooked. Okay. So once again, let's do some plotting. Let's go, let me see, 1, 2, 3, 4, 5, 6. Let's go 1, 2, 3, 4, 5, 6. I don't believe we get any negatives with this, so we probably don't have to do too much with the negative values. Okay, so now I'm going to graph this. So I'm going to go 2, 6, so over 2 and up 6. So it should be about there. Now I'm going to go over 0 and up 1. Oops. Right there. I'm going to go over 0 and up 0. Right there. And then I'm going to go over 2 and up 0. Right there. And I'm going to go over 6 and up 2. So that would be right about there. So let's see kind of what this might look like. Oops. Let's see. We're going to get something like this. Just bear with me, guys. It's hard for me to draw with this. Something like that, maybe. I think I drew it pretty bad. Maybe I can do it like this better. Let me see, do I have a wrong value in here? Let me double check this. So I go 2, I plug -2 in. So if I plug -2 in, then I should get 4 minus 2 would be 2. 4 plus 2 would be 6. Plug -1 in, I get 1 minus 1 is 0. That would be 1 plus 1, which is 1. Plug 0 in, we get 0, 0, 0. Okay, plug 1 in, I get 2. Plug 1 in, I get 0. So I got over 2. So yeah. Something like that. There's some kind of loop over here. Okay. Oops. Okay. I did it again. Okay. So now when I'm going to count my time frame, I'm going to go to -2. Where was -2? Well, -2 for my t was over 2 up 6. So I'm actually working my way this way. All right, so I'm in that orientation. Sorry about that, you guys. It's a little harder for me to draw for some reason. Okay, so let's take a look at something else. So in these previous problems, I chose my t value. Sometimes it might be given to you what part of the interval you're supposed to find. But in general, plot about 5 time values when you're working with these. Sometimes we can eliminate the parameter to get a Cartesian graph. So let's look at one of those. So say we have, so it says, let's use, so we're going to use one of the ones we worked with before. Use t equals y minus 1 and x equals y minus 1 squared minus 2 times y minus 1. Oops, I'm telling you guys the answer. Okay, hold on. All right, so let me go back up to this original one, t squared minus 2t. So we have x equals t squared minus 2t, and we have y equals t plus 1, okay? So I would want to say, let's see, sometime. So I say find the Cartesian equation for the given parametric equation, okay? So what we see is that we know that y is equal to t plus 1, so that technically means then that y minus 1 is equal to t, right? So y minus 1 is equal to t, so that means I could now take t and substitute in y minus 1 into the other equation. This is called eliminating the parameter, okay? So then this would leave me with x equals, let's see here, y minus 1 quantity squared minus 2 times y minus 1. So x equals y squared minus 2y plus 1 minus 2y plus 2. So x equals y squared minus 4y plus 3. Okay, so this is a, some people call it a horizontal parabola. Okay, you could also call it a left-right parabola, one that opens left or opens right. In this case, this one I believe will open right. And we could do the same thing that we've done for all parabolas. We could find the x-intercept, the y-intercept. We could also find the vertex and the axis of symmetry. But look right here. If I had continued on with this graph, look what I would have created. I would have created a sideways parabola or a right facing parabola that would match this. So sometimes it's easier to convert the parametric equation to a Cartesian equation so you kind of see what you're getting yourself into. So sometimes that'll help, okay? All right, so let's take a look at another one. Okay, I think that's enough for graphing. Let's look at, sometimes we might want to do the same with plotting, but there's a portion of it that we may need to do where we have to clean things up a little bit. So it says plot the following, and you guys will see what I clean things up. Following parametric equation. Okay, for 0 is less than or equal to theta is less than or equal to 2 pi. Okay, so we have x equals 2 sine theta and y equals 2 plus 4 sine squared theta. Okay, so in this case, our parameter is theta instead of t, and this happens a lot with theta. Okay, theta is also used oftentimes for parametric equations as well. Okay, well, let's first let's eliminate the parameter. Okay, so that means we should take 2 sine theta, and we should be able to solve for theta. So we have x over 2 is equal to sine theta. Now I could try to solve for theta if I wanted to, and I would have arc sine of x over 2 is equal to theta. But technically, I currently know that x over 2 is worth theta. So take a minute and plug this in for sine squared. So that means we have y equals 2 plus 4 times, now this is sine of theta squared, so we're going to use x over 2 squared. So this becomes y equals 2 plus, well, this is 4x squared over 4. So y equals x squared plus 2. Okay, so hopefully you guys see how I did that. Okay, if not, ask me in the next meeting. All right, that you can eliminate the parameter like this. Now, there's a problem with this. Okay, now we technically have to put some restrictions on x and y. Okay, now think about this real quick. Originally, they had said 0 to 2 pi, so we're just doing one full period of a normal sine function, right? And you're saying that y is equal to x squared plus 2. Okay. However, you know that this is a parabola that goes up 1, 2, and goes on forever, right? That would be what it normally is. But there's some restriction put on it because of where it came from, because of how we built it, okay? So we need to talk about x squared plus 2 and x over 2 equals sine of theta. So I need to talk about this, okay? So I'm going to put x over 2 is equal to the sine of theta. Now, what's the biggest number the sine of theta could ever be? The sine of theta at most could ever be 2. I'm sorry, it could ever be 1. So that means that x could only ever be 2 in this problem, right? So we know since sine of theta is always less than or equal to 1, then that means x over 2 at most has to be, has to also be less than or equal to 1, okay? So then that means that x is less than or equal to 2, right? Because it goes along with the fact that sine of theta is equal to x over 2, all right? Now, what's the smallest that sine of theta could ever be? Sine of theta could be -1. Well, wouldn't that mean then that x could be -2 or bigger? So we know that x over 2 could also be greater than or equal to -1. So then x is greater than -2. Okay, so we're going to take this, and we're going to put x smack dab in the middle. And we're going to create a compound inequality. Oops, you know what? This is all kind of close together. Let me do this in green. So we have -2 is less than or equal to x is less than or equal to 2. Okay, so this is how we're going to talk about our x. Okay, now think about this. If x is always between -2 and 2, then doesn't that affect what y could be, because this is the x right there? So now we have to come over here and adjust our y. So what's the biggest x could be? The biggest x could ever be is 2 in this problem. So that means y equals 2 squared plus 2, which is 6. So that means that the biggest y could ever be is 6. And then what's the smallest it could be? So we do y equals -2 squared plus 2. Wait a minute. Oh. Well, that would just give us 6 again. However, what if x were 0? If x were 0, then we would actually get 2. So y has to be between 2 and 6. So because of the way we built this problem from this idea right here, this is how we completed the problem and we eliminated the parameter. We have to have certain restrictions put on our x's and y's based on this probability, or based on this problem being true, okay, of x over 2 equals sine of theta. All right, so when we go to graph this now, we have to be a little bit more careful. Let me get a little graph here. Okay, and we're just going for a sketch again. So once again, I'm going to use the parametric one, or I'm sorry, I'm going to use this little table here. I guess I should have wrote it on the other side. Theta, x, and y. And I'm going to plug in 0. I'll use ones that I know, pi halves off the top of my head, pi, 3 pi halves, and 2 pi, right? So when we plug 0 in for our x up here, we're going to get 2 sine of 0. The sine of 0 is 0, so we get 0. So you guys should be able to fill this out. I'm just going to fill this table out for you. Pause it if you'd like to complete this. Okay, so hopefully you guys are back if you paused it, and you're now at these values, same as me. Okay, so 0, 2, 0, -2, 0, and 2, 6, 2, 6, 2, 2, 6, 2, 6, 2. Yeah. So I'm gonna, you know what? I better go by twos. 2, 4, 6. 2, 4, 6. 2, 4, 6. 2, 4, 6. Okay, so let's see what we got here. So I'm going to go over 0 and up 2. Let's put a point right here. I'm going to go over 2 up 6. Put a point right here. I'm going to go over 0 up 2 again. Put a point right here. I'm going to go over -2, and I'm going to go up 6 again right here. Oops. Oh, that kind of, it's a little bit off, huh? It's not very symmetric. Well, hopefully you guys get the idea. And then we're going to go -0 up 2, and then -2 comma 6, and then back to 0, 2. So if we weren't paying attention, we would just think that it's this graph like this, right? We would just think it's a triangle. I'm sorry, an absolute value. However, we know from here that what shape is this? We know that this shape is a parabola. So even though the graph might be a little deceiving to us, we know that we have a little parabola right here. Okay, and I'm not going to go above 6 or below 2 in terms of my y values, and I'm not going to go to the left more than -2, and I'm not going to go to the right more than +2 because of all the restrictions I had to put on my x's and on my y's. Okay, and in terms of direction, so let's start with the smallest theta, 0. Okay, so when we plug in 0, we go over 0, 2. And then let's see what direction the next one is. And we go over 2 up 6. So we must be going this direction. Okay. And then we'll obviously come back around and go the other direction. This will just keep recycling. Okay. So hopefully you guys understand why I had to put boundaries on or restrict the X and the Y, because it just wouldn't make sense with X over 2 equals sine of theta. Okay. So let's kind of close that section off. Okay. Okay, so now I'd like to take a look at another graph. I'd like you guys to sketch the curve. Represented by X equals sine t and Y equals cosine t. Okay. And I'd like you to also write this equation in rectangular form as well. Okay, so if we were to make our table, we got t, we got x, we got y. And we're going to do 0, pi halves, pi, 3 pi halves. And these are kind of standard. Again, if you need different ones, you can use different ones. And let's fill in the table for this. So plug 0 in. You guys go ahead and pause it and fill it in the table. I'll complete it while you're doing it. Okay, so now I'm going to graph this. Okay, so we go over 0, up 1. We go up, oops, I did it backwards. Sorry about that. Okay, so we go over 0, up 1. That'll be here. We're going to go over 1, up 0. That'll be about here. We're going to go over 0, down 1. That'll be about here. We're going to go over -1. That'll be about here. So -1, 1, -1, 1. Okay, and then we're going to go over 0, up 1 again. Okay, so we have what looks like a diamond or a square maybe. Okay, but you know that can't be the case. How do we know that? Well, we know this formula over here, sine squared t plus cosine squared t is going to be equal to 1. And if you guys remember back from a little bit of or from the original problem, it says that x equals sine of t. So this will be x squared plus y equals cosine of t. So this will be y squared equals 1. Well, you guys know this is a circle of radius 1. So there's no way this can be the graph. So what we're going to do is we're going to draw a circle of radius 1. And that's about as good as I can get it, guys. Okay, and now in terms of direction, well, let's see. We started up here at 0, 1, and then we went here to 1, 0. So we're going to be going clockwise. Okay, so that's the direction we're going with our curve. And these are supposed to be arrows. I just realized how ugly they were, but they are supposed to be arrows. Okay. All right, so that's the direction we're going. And we're going to limit the interval between 0 and 2 pi. In general, that's what you have to do for these problems. Otherwise, it would just go on forever and ever and ever. Okay. So now let's put here t 0 less than t is less than 2 pi. Let's do that. Okay. So now let's use knowledge to help us with another equation. Okay. So this one says sketch the curve represented by x equals 2 cosine of theta over 4, y equals sine, 5 sine of theta over 4. Given interval, let's see. All right, write this equation in rectangular Cartesian form. Write in rectangular or Cartesian form, okay? And then we're probably gonna have to find an interval you can work with on this, okay? So in this case, try to just, instead of building a dual, I'm gonna try to convert this parametric equations into Cartesian equations or into a Cartesian equation, and then discover what type of curve this actually is. Okay, so let's do some work here first. More than likely, because we're dealing with trig, you guys be writing over here sine squared theta plus cosine squared theta is equal to 1. Okay, know some facts. We know that x is equal to 2 cosine theta over 4. Okay, but that really means that cosine of theta over 4 is equal to x over 2, okay? And then we could square both sides. So we now have cosine squared theta over 4 is equal to x squared over 4, okay? And let's do something similar with y. Y equals 5 sine theta over 4. So we're going to end up with y over 5 is equal to sine of theta over 4. Now you guys should know, why am I squaring both sides? What makes me want that? Well, it's because I'm trying to get to the sine squared theta plus cosine squared theta equals 1. So we have this. Sorry about that. So this will become, let me clean this up. Sine squared theta over 4 is equal to y squared over 25. Let me see, y squared over 25. Okay, now we should be able to take this guy and put in there, and take cosine squared and put that in there, but use our replacement values. So we now know that sine squared theta plus cosine squared theta is equal to 1. So then what we're going to do is we're going to do y squared over 25 plus x squared over 4 is equal to 1. Okay, now this is a particular shape that you should know. This is now in Cartesian form or rectangular form. Sorry about that, I keep switching it. And I now know how to graph this. This is an ellipse. Okay, so this is an ellipse because it has a major axis and a minor axis. And I can go like this. Let's see, here we have, I'm going to use green. So we're centered at 0, 0 because there's nothing here or here. So we're centered at 0, 0. And we're going to go on the minor axis, which is the x-axis. We're going to go over 1, 2, and then we're going to go over 1, 2. Okay, so this is -1, -2, 1, 2. Okay, so we're going to put a point here, and we're going to point here. Then on the major axis, which is the y, because it has the bigger number in the denominator, this is going to go up 1, 2, 3, 4, 5. Put a point. Down 1, 2, 3, 4, 5. Put a point. And then we connect them. Wow. You know, guys, I'm going to have to extend this just because it looks so bad. I'm going to fix it. Oh, man. So let me clean these up. This should be 1, 2, 3, 4, 5. -5 right there. Okay, so that's our ellipse. Sorry, I can't draw. All right, so hopefully you guys have done ellipse before. And so just by putting it in Cartesian, I was able to eliminate the parameter, put it in Cartesian form, and it became something that I recognized. Okay, it became something that I'm comfortable working with. Let's see if we have another one here. Sure, let me give you guys one to try now. Okay, so why don't you guys do the same thing? Repeat the above for, and let's say x equals 1 plus 5 cosine 2 theta. And let's say y equals 3 minus 4 sine 2 theta. Really quick, you guys, I just remembered something. You need the direction that this is going. So we're going in that direction. We are going counterclockwise for this problem. And also we need to know the parameter for t to make one full cycle. Let's say we're going to make one full cycle. Okay, the way you guys do that, or it's not t in this problem, it's theta, is you take theta over 4 and you bound it by the normal boundaries of a typical sine or cosine function, which would be 0 to 2 pi, right? So then we just multiply everything by 4. And we will get our new value, which is 0 is less than theta is less than 8 pi. So this is actually our boundary. Okay. Hopefully that helps you guys. Whenever you have something inside the theta, you can just plug it in between the 0 and 2 pi and you can adjust it like that. Okay, so let's take a look at this other one and let's do a similar thing. Okay, so pause the video real quick and you guys try to eliminate the parameter, identify what this is, and then build the interval to make one cycle. Okay. Okay, so hopefully you guys are back. And once again, what do you automatically have in your mind? Sine squared theta plus cosine squared theta equals 1. So you're working with that. So this becomes x minus 1 over 5 is equal to cosine of 2 theta. And this one becomes y minus 3 divided by 4 negative equals sine of 2 theta. Okay. So this is actually x minus 1 squared. Well, you know what? I'll square both sides ahead of time. I was going to go through another step, but I think you guys can get this. So then this will be x minus 1 quantity squared all over 25. And this will be, or that's equal to cosine squared 2 theta. And this one will be y minus 3 squared all over 16. The negative ended up not mattering. And this will equal sine squared 2 theta. Okay. So now once again, we plug this into our formula over here, and we're going to say sine squared 2 theta is equal to y minus 3 squared over 16 plus x minus 1 squared all over 25 equals 1. So once again, hopefully you guys identified it with an ellipse, as an ellipse. Now this one is centered at 1, 3. Okay. You always take the opposite of the inside, just like with parabolas and stuff like that. So I'm going to come over to here and let's graph this guy real quick. Let's go 1, 2, 3, 4, 5. Let's go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And we're going to obviously have to go a little bit further, but I just want to show you guys how to kind of set this up. So we go over 1 and up 3. So I'm going to go over 1 and up 3, and I'm going to put my center. Okay. Now from there on the y-axis, which is in this case the minor axis, we go up 4. 1, 2, 3, 4, put a point. 1, 2, 3, 4, put a point. That's the minor axis. Now on the major, in this case, it's the 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And we connect our stuff. Oh man, it's brutal. And it's going to erase the whole thing. Yep. Let me give it my best shot here. Sorry guys, I had it and then it just went south. Well, I'm not going to mess with it anymore. That's about the best I can do, guys. So we have our ellipse, just like that. Okay. And it doesn't always happen as ellipse. It could be a hyperbola, it could be a circle, it could be a parabola, it could be all kinds of things. These are just the two that I happen to pick. So I just wanted you guys to have a heads up on that. Okay. And now I'd like to move forward onto derivatives in parametric. So I'm going to talk about tangent lines. Okay, so I think this video is getting pretty long at this point, so we'll probably make this our last problem. Okay. So if you want to find the Cartesian equation of the tangent line, we need a point and a slope. Okay, the slope means we need the derivative, just like we're used to doing. And it says, remember, this is the change in y over the change in x. So what if we have a parametric curve? So if we have x equals f of t and y equals g of t, then in order to find this, the derivative would be dy dx equals dy dt divided by dx dt. Remember, when you're taking the derivative of y with respect to t and the derivative of x with respect to t, we need to have the t accounted for, okay? So when you evaluate this at t, you will get the slope of the tangent line at that given t time, okay? So before we run out of time, let's look at one more example. So it says find the Cartesian equation of the tangent line to x equals secant t and y equals tan t at t equals pi 4. So they're giving us the time. They want us to check this out, okay? So the first thing we need to find in order to use this formula for the derivative, the first thing we need to find in order to use the formula of the derivative dy dx is we need to find dy dt and we need to find dx dt. So I'm going to have y equals tan t, and I'm going to have x equals secant t. Now I'm going to take ddt of both sides. I'm going to take the derivative of both sides with respect to t. I'm going to do the same over here. And this will become dy dt, which is good because I have a dy dt in my formula up here. And then over here, the derivative of tangent t is secant squared t, right? And then over here, this will become dx dt, and that is the derivative of secant t is secant t tan of t, okay? And then in order to find dy dx, I'm just going to write dy dx, and the formula says you simply write dy dt over dx dt. So I'm going to do dy dt, which is in this case secant squared t divided by dx dt, which is secant t tan t, but that's actually equal to secant t over tangent of t but that's really 1 over the cosine of t times the sine of t. Oh wait, but that's tangent in the denominator, so the reciprocal of tangent in the denominator is cosine. It's really cotan, right? Of t, cosine t over sine t. So then we see that our cosines cancel. And now we're left with 1 over sine of t. But you guys know 1 over sine of t is really cosecant, but I'll just leave it as sine of 1 over sine of t because I'm kind of comfortable working with that. So to find the slope, they gave us that the slope is pi over 4, right? So we go back up here, we look at pi over 4, sorry about that. And now we're going to do dy dx of pi over 4, which would be 1 over sine of pi over 4. But the sine of pi over 4 is the square root of 2 over 2, which if you multiply by the reciprocal, blah, 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 you can clean this up. You guys will get the square root of 2, okay? Now, all you just found was the slope of the tangent line. You now have to find the point. Well, that means that we need an x and a y coordinate with our m equal to the square root of 2. So what I'm going to do is I'm going to go back to the original, and I'm going to plug in pi force into my y equals tan t and x equals secant t. So remember, x equals secant t and y equals tan t, but we know that t is equal to pi over 4. So that means x is equal to the secant of pi over 4, and y is equal to the tangent of pi over 4. Well, this is what? 1 over the cosine of pi over 4. And we should know that. Let's see here. The cosine of pi over 4 would be square root 2 over 2, but since it's in the denominator, it's just going to be square root 2. And then let's see here. Well, we know tan of 45 degrees or pi over 4 is just 1. Okay, so we're looking good. So we have our point, square root 2 comma 1. We have our x and our y coordinate. Remember, we now have a point and we have the slope. Well, we can use point slope form to do y minus y sub 1, which is 1, equals the square root of 2 times x minus the square root of 2. And this is my equation of my tangent line. Okay, no big deal. So kind of thing that you have to memorize now is this new formula for dy dx. It's dy dt over dx dt. Okay, so I'm going to end the video on that, you guys, and we'll start some more of these in the next class and move on to more derivatives and more second derivatives even. So, all right, you guys, I'm going to end the meeting for today, and I will see you in the next class.